You're listening to Wurth Electronics What's Up Radio podcast, where each week we are seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and Wurth electronic technical specialists who are going to shine a light on interesting topics, such as energy harvesting, wireless power transfer, EMI issues, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Wurth Electronics What's Up podcast. Conducted emission measurements help us to understand the power converter performance, and this can be improved by EMI input filters. Now, in order to reduce conducted emissions efficiently, we need to understand the total noise spectrum, including the separation of common mode and differential mode. While running multiple FFT correlated with the time domain, an oscilloscope captures the noise results. And this way we can select the correct EMI input filters efficiently. In today's episode, we'll discover just how to separate the noise. We'll also give some practical measurement examples which demonstrate the iterative filter design process.
Our focus today revolves around the separation of common mode and differential mode noise using oscilloscope to enhance EMC filter design, resulting in faster and more efficient outcomes. As you can see on the far left, I have with me the powerful Rohde & Schwarz RTO6, known for its lightning-fast FFT update rate. And right beside it, we have the newer MXO4, boasting an even faster FFT speed. The journey of integrating oscilloscope into EMI measurements has been remarkable. Before we dive deeper into our topic, let's take a moment to explore EMC and why oscilloscope plays a vital role. Do you recall the days when driving and listening to your favorite radio station could be interrupted by a strange doo-doo noise? Often, a message or a call on your phone followed these interruptions. This is what we refer to as interference. Fortunately, such experiences are very rare today, thanks to substantial effort aimed at minimizing interference between electronic devices. Electromagnetic interference, or EMI, is typically unintentional but can emit signals that potentially disrupt other electronic devices. To mitigate this, regulations are in place to prevent or at the very least, limit such interference. In this context, we have the aggressor and the victim. Interference can propagate through the air or travel via shared electrical lines between the devices. The source of disturbance can be a magnetic or electric field, and it can couple in various ways. Ultimately, it reaches the victim device, impacting its performance or potentially causing failure and damages. Historically, EMI has led to significant issues, including product rejections, reduced yield, and in severe cases, harm and loss of life. Today, as the demand for powerful computing and high bandwidth communication system grows, circuits and systems are becoming increasingly complex and integrated. This closeness of components increases the risk of interference, pushing the boundaries of electromagnetic interference. This is where electromagnetic compatibility, EMC, regulations comes into play, serving as a guideline to ensure devices and systems remain robust when subjected to disturbances while emitting very limited interference. Every product and system must conform to these specific requirements of its industry. What is acceptable in consumer devices may differ significantly from what is required in medical or aviation applications. EMC ensures that interference and susceptibility are well balanced. EMC compliance primarily focus on electromagnetic interference, EMI, and electromagnetic susceptibility, EMS. These are branched out to examine conducted and radiated emissions. For instance, when testing for EMI, we subject a device under test to both conducted and radiated emission assessments. Conducted emissions involve isolating the device using a line impedance stabilization network, LISN, to channel the noise to the EMI receiver. Radiated emissions use an antenna to capture the noise emitted by the device under test, which is then fed to an EMI receiver for measurement. While the concept is straightforward, the setup can be challenging, as depicted in this diagram illustrating a compliance radiated emission test. Typically, compliance testing occurs in dedicated labs conforming to established standards. However, there's a growing need for pre-compliance testing in individual labs, as compliance tests can be time-consuming and often only provide pass or fail results without offering guidance for debugging. Moving one step further, EMI debugging is becoming more and more common, especially for power-related circuits. Solutions to resolve EMI issues often involve the addition of capacitors and chokes, which occupy PCB real estates. Hence, it's advantageous to address these issues during the early design phases. In terms of tools, various options are available. A compliant EMI receiver designed to adhere to industry standards offers the best sensitivity and is preferred choice for testing. However, if the lab setups are not compliant or not ideal, a spectrum analyzer can be considered, as it offers high sensitivity and frequency selection. Albeit not on par with a receiver setup, but lastly, you can also consider an oscilloscope equipped with an FFT and spectrum analysis capability that are valuable for debugging. Of course, despite they have inherent noise and their limitation. I've borrowed this slide from a colleague at Wurth Electronics because it simplifies the understanding of noise sources. A low-frequency noise typically originates from fundamental waves and controller harmonics, and is very dominating in conducted emissions. Conversely, high-frequency noise is often radiated, particularly in power circuits, where it may be associated with the fast and high spikes of Schottky diodes. Broadband interference, on the other hand, usually combines conducted and radiated elements originating from switching edges and parasitic resonance. Today, we'll focus on conducted emissions. If you're interested in testing and mitigating radiated emissions in your design, keep an eye on Rodet and Short's events, as we regularly conduct training sessions tailored to your needs. EMC filter design emphasizes on conducted emissions because they are more accessible for lab testing, especially when related to power circuit, which often require design adjustment and impact a broader footprint. Conducted emissions involve noise traveling through the main circuits, particularly in power circuits. Two main noise choices are the common mode and differential mode noise. Differential mode noise occurs when the noise moves in the different directions between the active and neutral lines, forming a return path. Common mode noises, on the other hand, flows in the same direction in both the active and neutral lines, returning through the earth line. Understanding the nature of these noises simplifies effective filtering. However, when we use the two-port LISN, it taps both positive and negative lines, while a receiver typically only has one port. This setup allows us to measure magnitude and frequency accurately, but does not distinguish between a common mode and differential mode noise. Here is an example of using the Rohde and Schwarz FPL 1000 spectrum analyzer. By observing the differences in noise between the listened output on each of the conductor, we can guesstimate the presence of differential mode noise, which is encapsulating the common mode noise. But can we precisely determine the common mode and differential noise in these figures? Let's revisit the circuit. We can simplify the listen into capacitor and inductors with Vp and Vn as noise outputs, determined by 50 ohms. Yeah? The device under test, or the DUT, is a DC to DC switch mode power supply. Noise must pass through the earth plane and return to the converter. Differential mode noise creates a return path between the Vp and Vn lanes. With the right calculation, it is possible to determine the common mode and differential mode using the value we get from Vp and Vn. So, with an oscilloscope, the key advantages lie in their multi-channel configuration. This allows us to utilize powerful enough hardware to set up to implement the necessary formula by measuring just Vp and Vn, and enable us to deduce both common and differential mode noise at the same time. It's important to note also the ideal oscilloscope should support multiple FFT and possess a low noise front end. These features ensures a better alignment with the performance of a test receiver or a spectrum analyzer, leading to significantly more accurate results. Another advantage of using an oscilloscope is its ability to display both time and frequency domain. This provides us valuable insights into the behavior of the device under test. While oscilloscope may introduce some noise, it's not as critical in a debugging context as compared to a compliance setting. As engineers, having visibility into noise characteristics allow us to quickly experiment and trial and error to identify possible fixes. Now, let's take a look at conductor emission setup. At the top, we have an NGP power supply feeding into a listen, which connects to the switch mode power supply's device under test via the red and black wires. You can see that. On the left, of course, you can see the power supply, the NGM, acts as an ELO for the switch mode power supply output. From the listen, you can observe we also connected the coaxial cable feeding into the RTM 3000 oscilloscope. Alternatively, you can also replace the scope with the powerful RTO6, offering a superior signal fidelity and exceptional processing capabilities to handle the Vp and Vn for noise calculation and characterization. Let's delve into understanding how an EMI filter circuit works. There are different approaches to handling conductor emissions. It can involve a circuit designed as part of the power input of the system. Alternatively, in cases where product has failed in the EMC labs and didn't account for an EMI filter circuit, a quick fix can be achieved with a ferrite clamps. While ferrite clamps offer a fast and effective solution, they may not be cost-effective if every inlet cable requires one. Turning our focus to the EMI filter circuit, the design of X capacitors and Y capacitors are easily incorporated into the system. Here's how they function. When dealing with differential mode noise, X capacitors create a low impedance path for the noise to return to the neutral line. Similarly, for common mode noise, Y capacitors provide a shorter pathway back to the source, thereby reducing the noise flowing in and out of the tested product. The challenge lies in finding out the appropriate frequency at which the capacitors should filter out those noise. On the right-hand side, we have what's known as a common mode choke. These chokes are also highly effective in addressing conductor emissions in the system. Looking at the picture, you can see various designs of these chokes from Wurth Electronics. They consist of two coils wrapped around a ferrite core or maybe other material. And here's the intuitive part. When dealing with common mode noise, the two inputs with the same direction will induce magnetic field that flow in the same direction. that behave like an inductor, impeding the flow of current. Essentially, it's like a filter, converting unwanted energy into heat and therefore reducing common mode noise. When dealing with differential mode noise, the coil induces magnetic fields with opposing directions, effectively cancelling each other out. A very smart concept to handle conductor emission. However, it's important to note that due to their size and inductive nature, common mode chokes may not be a preferred choice for many designers. In our case study, we will concentrate on assessing the impact of X and Y capacitors. Wurth Electronics also offers a specialized filter design kit. They are a wonderful resource for testing the effectiveness of various filters. This kit includes X and Y capacitors, as well as common mode chokes of different sizes and material to tackle different frequency response. It enables us to easily swap out components and determine which filter works best. Another reason why we did the experiment with common mode chokes is that the filter board typically requires soldering components in place, making it more convenient to use sockets for capacitors, but for the common mode chokes, it will be much more difficult. Next, let us explore how this filter impacts scope's measurements. So on the scope display, at the bottom, you can see that FFT is displayed on the mask channel, which uses the formula that we defined earlier that can help us determine differential and common mode noise. And by using an X capacitor to filter out the DM noise, the oscilloscope clearly demonstrates the improvements. Similarly, if we apply a Y capacitor, it yields a very noticeable result with reduced noise and an improved overall noise flow. When both capacitors are employed, the noise reduction is even more apparent. It's worth mentioning that to enhance the FFT quantification, we can increase the sensitivity of the oscilloscope channels, allowing us to make the most of the ADC capabilities. Well, this method is effective, but not everyone may have access to high-quality oscilloscopes. Is there an alternative hardware solution? Indeed, there is. It's called a noise separator. Some listeners are equipped with such a circuit that is designed to couple common mode noise and differential mode noise into different ports. Alternatively, with a bit of DIY tinkering, it's possible to create your own noise separator. However, it's important to note that this DIY approach requires a wide band RF transformer and a very high quality resistor for impedance matching. But the good thing is with this approach, you can use a receiver or spectrum analyzer to measure both common and differential mode noise without the additional computational steps. In conclusion, I want to emphasize that an oscilloscope is an excellent tool for debugging purposes in scenarios like this. While it offers valuable insights and the ability to experiment with fixes, there are various setup details that can influence the measurement. This includes the vertical scale settings, the noise level, and the presence of a ground plane, which is providing the return path for the common mode noise. And the adherence, of course, the sample rate to the Nyquist requirement.
You can check out the oscilloscope discussed in today's podcast by simply clicking on the link available in the description or visit the Wurth Electronic YouTube page. Those links will take you directly back to Roden Schwartz, and those are the experts in oscilloscope design. For easy EMI filtering, visit Wurth Electronic online to find the full filter design kit. You can order your kit directly from the website. You can also check out the complete lineup of EMI filter components such as ferrites for PCB, cable assembly, filter chokes, common mode chokes for extra low voltage and data lines, and also chokes for mains power lines, ESD protection, surge protection, and so much more. We understand that some videos and images are not available on all streaming networks, so to replay the entire podcast with the video, please visit our website at www.we-online.com/podcast or check out the Wurth Electronic YouTube page. You're listening to Wurth Electronics What's Up Radio podcast, where each week we're seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and Wurth Electronic technical specialists who are going to shine a light on interesting topics, such as energy harvesting, wireless power transfer, EMI issues, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Wurth Electronics What's Up podcast.